Thank you all for coming. I know this is the last talk for today, and we'll power through and make sure that we're finishing on the right momentum. So some of my street creds, my actual street creds. So I've been doing vulnerability research for 15 years, mostly focusing around vulnerability finding and exploitation. So my own just background is I've exploited just dozens of bugs, both in open source software and closed software. So I have a lot of intimacy with software vulnerabilities, just different types of vulnerabilities, what it actually means to find a vulnerability and fix the vulnerability. And in recent years, ever since kind of ChatGPT came out, I was obviously intrigued, and I am still continuing to experiment around how LLMs are actually helping with vulnerability research and with just different aspects of vulnerability management in general, which is what this talk is going to be about. So nothing still security related, don't worry about it. It's not a marketing talk. It's more of a technical just conversation and dialogue between likely minded people about how LLMs are actually grounded and are helping us today dealing with various aspects of vulnerability management. So today, again, as I mentioned, just challenging some of the hype. You know, a bunch of the vendors, even here in this conference, are going to tell you that LLMs are what will help you solve the issues that you have in your organizations. I'm here to claim that, well, no, this is not the case. We ran a few experiments. You know, I'm a hacker. I'm not one to take things at face value. So in order to just talk about what I am talking about today, we just ran some experiments using different models, I gave this talk half a year ago, and then we ran it on an older model. Now we redid the experiments with newer models. So just sharing some of our anecdotal evidence. It's not a research paper, not kind of the same level of scrutiny. So don't expect that, but it is interesting nonetheless. And yeah, the third point, which is interesting as well, is how to make the most out of LLMs if you want to integrate them as well as part of your daily work, doing vulnerability research. So starting out, what was important for me before engaging with LLMs is really trying to understand what are the limitations today, and what the community and what the research community is telling us that LLMs are not good at. So luckily enough, for my sake, and here we can see it on the bottom of the source, is that someone already did the work for me, and they already reviewed existing research papers and state-of-the-art results on this specific field of a survey of vulnerability detection techniques and insights. So what the research paper is teaching us is that existing LLMs have a real challenge around scoping and the complexity of vulnerabilities. So they're quite decent at dealing with very simple vulnerabilities, few lines of code that are vulnerable, but as soon as the scope starts to become more complex, they're failing quite quickly. But the paper doesn't really discuss what is the exact fine line between those two. Second, and it's also in some way a continuation of the first point, where the LLMs don't understand the program flow. Like they might hallucinate that they understand the program flow. They might write with confidence that this is how things are working, but in reality, they don't have an internal Turing machine that is able to really execute those commands and the different parts of the code and translate into something tangible and realistic and grounded in reality. So that's definitely just a technical gap that I assume down the line can be resolved just using taking runtime information and just feeding it to an LLMs. But regardless, this is kind of an existing gap. And the third major gap is around the LLMs just failing altogether in detecting logical bugs. So not just the regular Stack Overflows or buffer overflows or double free vulnerabilities. So any of the quote unquote simple vulnerabilities, so it's fine, but as soon as it's a logical bug and a logical mistake that the developer introduced, they are failing miserably. So as I said, we're hackers, so we're going to experiment. We ran 4 different experiments for this one. The first one, the most obvious one, is around identifying CVs. So how well can an LLM actually detect an unknown CV in a code? The second experiment, which is the other side of the first experiment, is how often they're mistaken. Because those of us that have used automatic vulnerability scanning tools probably are aware that there are a lot of false positives. So we want to measure if there is an improvement if we're using LLMs. Third point, which is somewhat unique to LLM, which wasn't possible before, is actually around the creation and assessment of security patches. So either if we want to create a patch for a known vulnerability, we know that the vulnerability is there, we know the description of it, we know the risk, and now we want to instruct the LLM how to fix it. So this is obviously very useful with internal code that you want to make sure that the fixes are introduced, but also the other side of it, which is assessing if a security fix is actually mitigating the risk. So this is the third part. And the fourth experiment that we did was around identifying malicious commits, which if you've been using open source kind of in your environments, you obviously know that supply chain risk is a big risk and something to be kind of taken into consideration. So one of the things that we figured just ahead of time that LLMs actually have a very good potential at identifying malicious intent behind commits. So this is the fourth experiment that we ran. All right, some few line items, order of business, just before we jump in. We focused, and again, because we didn't try to just achieve a new state-of-the-art results, like we just wanted to just verify how things are working, how well they're working, we tried to keep it simple. And that means simple CVs, meaning they are only affecting one file, and that file only has one on CVs, so no kind of mistakes or confusions between a few CVs that might affect it. Tested with Claude's Sonnet 4 on this specific iteration. 400 different CVs. And just as, again, point of information, running the entire suite of 4 different experiments cost us about $1,500 per run. So quite expensive, like if you want to do it personally. But yeah, for an organization, it's something that is obviously more feasible. So let's go ahead. So first experiment, identifying CVs, taking our data set, giving the LLM the code before the patch. And also what we noticed was helping the LLM improve slightly is also providing it the list of CWEs, meaning an explanation of what different types of vulnerabilities exist out there. So, and this is maybe a point that's worth kind of lingering on, because what you hear me kind of saying throughout this specific talk is that context is king. We are assuming, because the LLM is trained on the entire internet, that it knows everything. But the fact that it was trained on something, there is a very big gap between it understanding and correlating what you're doing right now to something that you've trained on. So if you want a vulnerability, the LLM to look at vulnerabilities and identifying vulnerabilities, you should probably tell it what type of vulnerabilities it should be looking for. If you're researching a specific mechanism or specific protocol, then including the protocol RFC for the LLM to have as a context is something that is very important. So I'm just going to repeatedly state it, that context is king. So just this is the reason. And when you are working with LLM, this is the #1 thing that you should be taking into consideration. But back to the point, we provided it the code before the patch, list of CWEs. And we asked the LLM to provide us with whether a CV was detected. Obviously, in this case, we expect it to be always true, but this is what we asked it. We asked it also to categorize which CWE the vulnerability is for, to understand that it really understands the vulnerability. Third, to provide the vulnerable method. So this is a way for us to compare it with our database and ensure that it didn't find vulnerabilities in just the wrong, maybe it's the right CWE, but it's the wrong place and the wrong function. And the fourth point is just explanation, to provide an explanation for its thought process, because we, as part of our review of existing research papers, what was just stated throughout is that if you ask the LLM to provide an explanation, it just provides better results. This is just as simple as that. So we just rolled with it, and we always ask for an explanation, and also it helps with debugging and just knowing whether something goes right or wrong. All right, so before I jump into the results, I think we'll do a short quiz. So raise of hands, how many people think that the LLM got right over 50%? 1, 2, 3. All right, cool. Between 25 and 50%. All right, I think majority of the room. Under 25%? All right, 3 people. 19% of the time it identified the right CWE, 16% it identified the correct method, and the correlation of both is 4.6. I don't know, I don't trust that. If I had to use it to identify vulnerabilities, obviously it's abysmal results, and this is just using the latest state-of-the-art model. So yeah, it failed quite badly, just giving a file, asking it to find a CV without any context beyond that. So keeping it neutral, yeah, really not working. So I would avoid just using LLMs out of the gate to identifying CVs without any sort of direction or really something beyond that will be able to just make it more predictable. Second experiment, false positive rates, which is very important because even if the first experiment turned out to be having better results, if at the end of the day you have 100 findings and out of them only one is relevant, it's just a waste of time for everyone involved. And also, by the way, if you take a look at other kind of presentations on the matter and results on the matter of people that claim that the LLM managed to get some nice results, usually you would see that they're running it on the same code or the same function 150 times. And then a human is verifying and looking at every single iteration of all these 150 iterations. And then only in one of the iterations, the LLM managed to get it right. So there is definitely a gap here in just a matter of consistency. So false positive rate, the experiments was giving the LLM the data set of the same CVs, but now with the code after the patch, meaning that there is no vulnerability here. But essentially, it was the same prompt. We asked it after the full code was fixed whether it can find a vulnerability. So this was just our method, and yeah, essentially we ran it twice. One keeping the language of the prompt neutral, the same way that we did in the previous experiment. And the other, we tried to be more confident in how we're telling the LLM, hey, there is a vulnerability here in the code and please find it. So just introducing some bias into the actual prompt. Here the results is that the interesting part is that you see that 44% false positive, but more interesting is that once you introduce some bias into the prompt language, it just jumps instantly to 55%. So quite a big gap, and you should be very careful in how you're structuring your prompts, because if you're too leading, questions in the end maybe. So if you're too leading in the language that you use to prompt, yeah, the LLM will just say, hey, I'm sorry, yeah, there is a vulnerability here, so be careful. But yeah, essentially 50% reliability, slightly better than the previous time, but obviously still not good enough in my opinion. Third point, creating a security patch. This one it was slightly more complicated in terms of setup, but we provided it the same data set. We provided it the file code before the patch, but then we also provided the actual explanation about the vulnerability. So we gave it the CV description, the function, the actual code of the function before the patch. So we provided it with a lot of context, just so, again, context, making it more concise and making sure that it's looking at the right places. And then we asked the LLM to create a patch with explanation, of course. But then on top of it, we also introduced another layer of LLMs, again, to check out the assessment of how well can an LLM assess a security patch. And we used the LLM as a judge to assess the validity of the patch that was just created a step prior. And we asked it to tell us if it's equivalent or not, and also the explanation. All right. So out of those, and since it was more difficult setups, it is on a more limited data set than the 400. So we tested it on 84 different CVEs. And we, again, compared the original patch for the correctness. Sadly, however, if we're talking about assessment, the judge was wrong in about 40% of the time. So I don't know, if 40% of the time you cannot trust if what it tells you is true or not, like you cannot really trust it. So we just had to manually test everything. And this is part of the reason why we did 84 instead of 400, because like going over them one by one is time consuming. So yeah, 60% of accuracy in terms of the assessment, and yeah, it wasn't that great. So jumping forward, so for the fourth and final experiment, identifying malicious commits in the JavaScript dependencies. So the concept goes as follows, and like we can leave the diagram for a little bit. How software development works is that different people are committing different lines of code into public repositories, and then those commits are being integrated and merged into the public upstream. So what essentially the concept was is that you take two different versions, and then you break them down to all the commits that were introduced, and then one by one you feed those commits into an LLM to try and find any malicious behavior in those commits that were introduced between the versions. So we wrote just a small tool for that, and we tested it on 12 real life examples of commits that were discovered in the wild. So we did that because obviously just running it on random open source code, like it will normally just not result in anything interesting, because in general there are not a malicious code in open source software. Again, in general, don't take me for it, but yeah. But essentially, yeah, out of those 12 malicious commits, and after about 8 iterations on the prompts, mainly because those 8 iterations were around reducing the amounts of false positives. We had to, for example, we had to instruct it to only detect malicious code and ignoring potential vulnerabilities. Because when we started out and we said malicious, and correctly, I would say it also flagged for potential security issues, which, if you think about it, it's the correct approach. Because, for example, if I would be the one that would be introducing malicious intent into open source components, I would not just download the raw binary and execute it. This is just every supply chain tool out there in the market will be able to detect that kind of behavior. So that's not very interesting. What I would do instead of that is that I would introduce a vulnerable behavior into this component, because then it makes it much harder to detect. So just prefacing it out there that this kind of technique is still lacking in identifying this kind of malicious attacks. But so yeah, it's still susceptible to intentional vulnerability introduction. But regardless, 100% detection for the cases of real scenarios where it was detected. Although I will say that again, because those are the ones that have been detected, we have some bias here in the results, because if they were detected, then yeah, that makes it easier to detect. But still, if you are implementing this kind of approach or kind of thinking about it and experimenting with it, what you should be aware of is that it's susceptible to prompt injections. So imagine the commit that you're reviewing, there is a prompt injection. Like it's problematic. And as we see now with LLM browsers, like it's all over the place. Prompt injection is something that no company has been able to solve so far. So just be mindful of that. Also, when you implement, just take into consideration that it might not be a single commit that is malicious, but it might be just spread out across across time. So again, something to take into consideration. And internal vulnerability introduction I mentioned, but the fourth, last but not least, is bad practices. We noticed that the LLM had the tendency for just taking bad coding practices and just flag them as malicious intent because the developer thought it's a good idea to download just a file and just execute it directly from the internet, but it doesn't necessarily mean that it's malicious. Yeah, it doesn't, and it also doesn't mean that it's not a bad coding practice, but again, for our purposes, it does mean that there are some false positives around that area. Cool. So kind of summing it all up and some tips and tricks for how LLMs can actually be used effectively, even given kind of some of the abysmal results that I showed you previously. They do show promise at suggesting security patches. Like out of the results that we had, like this is where we had the most amount of success in terms of the accuracy and obviously the time that it saves for the developers that need to be involved. But I wouldn't trust them to assess them. So that's kind of one thing. The second, which is more about SEAL in the sense that we are using it internally as part of our backporting process. So we have an existing patch. We just need to make sure that it's compatible with the previous version. So an LLM is actually like quite good at doing this backporting process given the right context and the right prompting. And the third point, which kind of saw for yourself, is that build your own malicious code detection engine is something that is quite feasible. I think for a lot of companies nowadays using LLMs is something that I would encourage you, if it's within your realm of responsibility, to build yourself. I wouldn't trust a vendor to do it because it's honestly, like even using kind of vibe coding, it took us less than a day to create this detection engine. And yeah, it's just something that I think it's cool to build yourself. So this is what I would do. Some more tips and tricks. As we saw, just avoid using suggestive language. If you do, you'll get less good results. I would not use an LLM as an end-to-end anything. I would only use it as a companion to a human when dealing with vulnerabilities and this in this scope where because of just the inconsistency and everything else that you see around it, so you still need the human in the loop. So there's that. And explainability, I mentioned in the previously, so I won't repeat it. But again, context is king. You think the LLM is the right context. It doesn't. Like just take the extra effort of like making sure that you're putting in the right context, the right background for what you're trying to achieve. So just as an example, if I'm researching protocols that has an official documentation, an official RFC, the proper instructions for how to implement this protocol, then I would feed it to the LLM when I'm researching this protocol and trying to identify vulnerabilities, because then it has the context of what the actual implementation should adhere to. So this is just something that I found myself helps elevate some of the results and actually get some cool findings with the help of LLM. But yeah, that's it pretty much. So thank you for your attention, and yeah, any questions?
I have a bunch of questions. I like the fact that you have provided a different lens to view that experiment of CV analysis. There were a few more lenses that I was looking for. The first one was, distribution of the context used. For example, you have a 100K token window. Did all of the context fit in it, or it was a multi-turn agentic kind of approach for all of your experiments?
That's a good question. So the gentleman asked whether we took into consideration the context and looking at context when we experimented with vulnerabilities and how much of the context was in use. So correct me if I misunderstood, but specifically this affected some of our design choices for the experiments and why we limited also just for single files. because we knew that if we'll start taking files that are, across, multiple files and stuff like that, like we will very soon hit this kind of context limit and things. So that's definitely a limitation when you're working with LLMs now for vulnerability management, where repeating to my context is king question is not just adding context, it's also eliminating context, which is the important bit. So don't just take irrelevant files and just toss them to the LLM. Don't take entire code bases and just toss them to the LLM. One of the things that have been proven mathematically about transformers and how they're working is that the farther that you get from the initial prompt and the initial tokens that you feed into the LLM, the more hallucinations are happening. So just be mindful of that. Keep it short to the point and be as concise as possible. And again, it's very hard to manage having this extra context and the relevant context and not having too much context, but this is kind of the technological phase that we are at, just dealing with LLMs.
Just a follow-up comment. Then the result of the experiment also becomes an artifact of the design you have chosen to test out the things, as in the design of that agentic calls and how you would summarize or attack the information.
Yeah, I would assume as much that again, like he asked specifically about whether our design choices affected the final results of our experiments, and yeah, for sure. Specifically, we chosen very friendly kind of limitations to the LLM and kind of like very LLM-friendly design choices. So we expected to get way better results, if I'm being honest, because we did it on very simple cases. In real-world scenario, where you have real vulnerabilities that are actually complex and not just stupid things that every scanner that exists today would be able to find, then yeah, like it starts to become even more ridiculous in the sense of what can actually be achieved. So yeah, it's definitely affected, but it affected it kind of in the wrong way. Like in a sense, like we thought we would get way better results when we introduced those limitations, but it didn't seem to be the case. Yeah.
Last question, language. Was it just Python or other languages also?
For some of the experiments, it was multiple programming languages. Specifically for the third one, the creating and assessing security patches, it was only in C.
Yes, yeah. That's a known challenge with LLMs, right? They're good at Python, but not good at other languages.
So specifically in vulnerability assessment and management related research papers, the majority of them is actually on C. Yeah, but just we can follow the source that I have in the presentation and take a look. But the research paper actually mentioned it as actually a bad point. Like as you said it yourself, like this is some of the results should be taken with a grain of salt because like it's only on specific programming languages and like there's a large skew toward a specific programming language. You are right in the sense that LLMs are very good in Python because a lot of the training set that they have is on Python, but it doesn't necessarily translate to vulnerability. Yeah, to vulnerability management. Yeah.
Thank you.
Yeah, sure. More questions?
I may have missed it earlier, but the LLM that you were feeding the data into, was that a custom trained LLM that you were using, or was it one of the code-specific LLMs?
No, Cloud Sonnet 4.
It was Cloud Sonnet.
Yeah.
Two-part question, if you don't mind. You mentioned at the start you fed CVEs. Was that CV identifiers, the metadata, and everything? So I'm going to miss that.
This part?
Yes, I think it was the one. Yeah, so the CVE.
So yeah, it's a CWE, not the CVE. And yeah, specifically, again, not to lead on the LLM, essentially. But yeah.
The other part of that question was you mentioned in the malicious code detection part that you had 8 iterations or a number of iterations over the prompt to get to that 100% mark. Did you do the same sort of iteration on the prompts for this?
Sorry, can you repeat this?
Did you do the same amount of iteration on the prompts for the first part of the test?
I'm not sure I follow. Sorry, can you, let's be here for a second. And
So the 8 prompt iterations that got you to the 100%.
oh yeah. Initially, it missed out on a few cases. Yeah, so kind of.
Those initial tests that you ran, did you do the same amount of iterations of the prompts to get your results, or did you just do a single prompt and then that was the results you received?
So the way that it was structured is that the testing suite included all of those examples, and then also obviously benign code that doesn't include any commits. And then when we ran it, we just stored kind of the statistics of like the false positives and true positives, and then we just iterated on that. So this is kind of how it worked. And most of these prompt iterations were not actually to bring it to 100%. It was more around eliminating the false positives as much as possible, because it was just out of control. Like if we would just use the first iteration, we would get something like 70% just false positives, something like that.
So that's for this case. But I'm referring to the first case where you're doing the CWE matching. Did you iterate with the prompts for that?
Yeah. In each of those experiments, we iterated on the prompts just regardless, but here I thought it was interesting to mention specifically because it was mostly around just eliminating the false positives and dealing with bad coding practices and stuff like that. And also I thought it was more worth mentioning because this is a part where I actually think, and as I said previously, that like you all can just go in and just implement yourselves and just do it yourself. So this is why I kind of spend more time actually talking about the implementation bits.
So on your 19% success rate for the CWEs, of those successes, was the LLM really good at one particular kind of weakness it could identify versus others, or was it more all over the place?
That's a very good question. Yeah. There were specific CWEs. As you can imagine, the more simpler ones, like those are the ones that it was just better at identifying it. But also like the reason like for the 4.6% of being correct on both and why we did it in that case is because what we saw is that oftentimes it just misunderstood what the vulnerability was. It was just like even like if it looked at the code, it looked at the right function, and then it would like just spit out nonsense essentially. So like it identified the completely wrong CWE. So this was just a simple quote unquote like hack for us to introduce an easier way for us to judge how the LLM is faring, because again, I guess 400 the different CVs, just reviewing, like, and we had to review them manually. So just doing that and comparing them all, like so we found that this just grounds it and enable us to understand if it actually understood what was going on or not, in combination with explanation.
You mentioned you ran your tests using an older version of an LLM, and then you reran your tests as newer versions came out.
Yeah.
Did you see an improvement?
Yeah.
A remarkable improvement?
No. Yes and no. So I gave this talk half a year ago. We've been using M1, so OpenAI model, and back then it was 11% on the right CWE, and 9% on the correct affected method, and 2.6% on the correct on both.
Yeah, like a doubling, you know?
Yeah. You're good at marketing. Yeah, maybe we should get you. Yeah. Yeah. So yeah, not that good of an improvement, but yeah.
Can you say more about, you had a recommendation to build your own tool right after telling us that this one did terribly. Can you say more about what you had in mind?
Yeah, so what I had in mind specifically is ignoring the areas around vulnerabilities, because again, in our experiments, again, take it as you will, you just get too much noise and too much nonsense for it to really be like complementary in the sense that where you automate it and you just trust the results. I am like encouraging you to use it as a research companion, as an assessment companion, and stuff like that, because it allows you to have the governance and the processes that are needed to actually make it work in that sense. But what I encourage here for you all to build is this part. And actually, news from yesterday, I think, is that Datadog actually announced just that this is just a new capability that they have built. So no, I've built it using vibe coding in less than 24 hours. So no, I would not pay for it. But yeah, specifically, this is why I mentioned that it has proven to me, and we're also, by the way, using it internally with Seal just for when we're looking in open source code and open source commits. But we see that it's working. Like compared to the other two where you just got very bad results, this is actually finding those malicious intents and finding those malicious commits. But yeah, like I would not, even like with those good results, I would not trust it without having a human in the loop. Like that's me personally in my risk acceptance for those things. But maybe it's just a seal in what we're doing. But yeah, it does remove some of the randomness in supply chain security in open source, because I don't know, for me the concept of developers just pressing update without reviewing anything and just pulling random things from the internet is way more scary than having some sort of layer in between that. So yeah.
So usually the output from LLMs are not deterministic, right? If you run LLM on the same code base, it spit out like the different results. Having that into consideration, what would be those percentages? Because you said like 19,
Yeah.
4.2 or something like that.
Yeah.
If you run like multiple times, those percentages would be different.
So for each of those experiments, we ran it 3 times and just average the numbers. Just because like the experiments themselves were quite expensive, as you saw previously. Like if it would be cheaper, we would run it 100 times and do the average. But this also kind of speaks to my point earlier in the conversation, where some of the groundbreaking results that people have reported and talked about using LLMs, like they ran it 150 times, on the same function, on the same thing. Had to review every one of those iterations, and then in one of those cases, it sped out something that was useful. So, like, yeah, there is randomness in LLMs, and you should definitely take it into consideration when you're implementing. It's statistics. Like, you need to apply statistics to it, essentially. All right. Thank you all for listening. You've been a great crowd. Thank you so much.